All right, and our second thing to talk about today is to start into, our introduction, to two-dimensional NMR, okay? So we've already learned about NMR, that NMR uses radio waves to detect nuclear spins, right? We know that in order to, when we interpret the data, we can get integration information. So this tells us the relative number of protons within a given signal. We learned about chemical shift, tells us something about the chemical environment that the proton or C13 is in, and we learned about splitting. Okay? So one-dimensional NMR, which is what we've done so far, really has two dimensions. Okay? It has the frequency domain, right? Chemical shift, and it also has intensity. Okay, so we call it 1D, but it really has two-dimensional. The 1D part of it really tells us that when we run the spectrum, there is a single time variable in the pulse sequence. So here's the pulse sequence here. We have a relaxation delay we talked about. We have our pulse, and we have a time domain, which is our acquisition time. Okay, so this is our one time variable in a one-dimensional NMR experiment. Okay, so if we're going to go to a two-dimensional NMR experiment or three-dimensional NMR experiment, we add another time variable within the pulse sequence. Okay, the times or the places where this is going to be useful is where our spectrum is really too complicated, and especially if we have too many overlapping signals, because we're going to be able to spread some of the signals over two dimensions rather than just one dimension. Okay, so it's going to spread out the interactions. All right, so if we look at a simple two-dimensional experiment, okay, here's a pulse sequence. We have some of the same parts that we had before. We have the relaxation delay. We have the acquisition time. We have our first pulse. This is usually going to be a 90-degree pulse. But we've added in this second time delay. Okay? And a second pulse. Okay, so in this experiment that we're going to do here, this is a second 90-degree pulse. Okay, so let's think about what might happen here. Okay, so here's our magnetization in the left. We draw this circle around here. If we first do the initial 90-degree pulse, yeah.
Is this like the test question more from last time, except now we're doing it with 2D? Or we're going to use the vectors to...
Well, we're going to use the vectors, yeah.
Okay.
The first one in I think the exam was how to determine the length of the pulse for the 90-degree pulse.
Okay.
Yeah, so we're using the same kind of vector analysis, but a different experiment.
Okay.
Yeah. So we just want to watch and see what happens to the spins. Okay? And we're just going to look at the spins at this point in the absence of any coupling or anything like that. All right? So we're going to do the 90-degree pulse, and so what's going to happen to the magnetization when we do the 90-degree pulse?
Should end up in the XY plane?
Right, it's going to bend down like this into the, if we do it around the Z, well, the X, here it said pi over 1/2 is, or pi over 2 is a 90 degree, it says in the X axis. So we're going to curve it around the x-axis, it's going to go down into the plus y direction. So our magnetization is going to be in this direction here. Okay? So now we're going to have our T1 time delay. And so let's start out just with the delta T1 equal to 0. Okay? And so now what we're going to do is we're going to do another, okay, we're going to do that, and then we're going to do another, well, let's do this in 2 steps.
Thank you.
I just got to be able to fit it all in here. Okay, so nothing's changed. Now we're going to do another 90-degree X pulse. Okay, so we're going to, again, we're going to rotate around the same axis. And so we'll rotate that down into the minus z direction. Okay, we went 190, went like this, and then we immediately did another 90. Okay, no relaxation or anything in between. All right, and so then we're going to do our acquisition and then our Fourier transform. And what's our signal going to look like?
Where's the detector at?
Yeah, the detector is always in the XY plane.
Okay, so
The
it
negative.
shouldn't see anything.
Oh, no,
Right, so it should be no signal, right? So we just get a flat line. Okay, so then let's do another experiment. Let's just start from there. Okay, well, they all start out the same. So we're going to do our delta T1, and I'm just going to put parentheses 1. So this is just some incremented time. Okay, and so what's going to happen is, let's say that this precesses a little bit over to here. Okay, so it's precessing around in the XY plane. And then we do our second 90-degree pulse. And so if this is sticking out this way, when it rotates around the XY plane, it's going to rotate down into this quadrant down here. Okay? So maybe I need to draw those a little bit bigger. So it's going to rotate from here down to here. And
XYZ plane?
it is the ZX plane.
Okay. A little hard to tell.
Yeah, so it's in this quadrant right here. Right? It would be in the plane. Here's the Z, and here's the X, right? Is this plane here.
So it wouldn't be any more Y properties, just X.
Well, it went from being,
XY.
so it went from out here. Remember, what we're doing is all we're doing in each of these is rotating around the X axis. Right, so if we had, this is hard to,
Yeah, it's hard to.
we have it like this, the XY plane was like this, right? And so it rotated a little bit this way, and then it rotated this way. So it's sticking down like this, right? So it should be in line with the X-axis,
Okay.
but there's some component that's in the Z direction and some component that's in the XY plane. Okay, so all we'll detect is the amount, or is the component of that vector that's still in the XY plane. Okay? Is there a bigger, you could do this maybe bigger over here. Right, so we went, so here's this circle here. We went from somewhere over here, and we rotated that down into this plane down here. So it's between these two, right? And the component of this, so it's down, there is some component of this that is still in the XY plane, right? And it's only the component that's in the XY plane, that's the only part of this signal that we would detect. Okay, so the important part here is that we have less than the full signal in the XY plane. Okay? So that means that our signal, after we do our acquisition and our Fourier transform, oops, that's a T, is going to now be, it's going to be some signal like this. All right, so let's see if we can, let's go to, yeah, I think the negative or the positive, I think it, yeah, I'm not sure. We could phase it whatever way we want, I think. Let's look at the next one and we'll see where we're going here. So let's do a second time domain. And this time we're going to let it process all the way to where it's in the, that was messy, in the plus x direction. Okay, so now we're going to do a second, so this is x, a second 90-degree pulse around the x axis. Okay, so what's going to happen in this case?
Drop straight down.
Well, essentially we have all the signal right here, and all we're going to do is rotate around it, and so it's going to just stay where it is. Okay? Because there's no component outside of this axis. It's all in that axis, so when it rotates, it's going to just look the same. But now we have all of the intensity in the XY plane. And so we would get a bigger signal. Okay, if we do one more of these, let's just do one. T1, the third time. And so this time we're going to let it go over to here somewhere. So it's gone past the plus x. And so when we do our second 90-degree pulse, it's going to rotate around here. And so now it's going to rotate up, right? Because we're rotating clockwise each time. Fell off. And so we're going to, oops. And so it's going to rotate. This is going to be hard to see as well. Up like this. And that's going to have some component still in the XY plane. Okay, and what I draw here, let's see, acquisition and Fourier transform is that I have just a smaller signal again. Okay, if we went further around over into these quadrants over here, then we'd end up going through, we'd go smaller and we'd go through 0 then. And so the point is that we have an oscillating signal, right? The intensity here is going from 0 to positive to big to small. It would go negative, and we would get something that looks like this. Okay, so this frequency 2, this comes from, on the last one, we have our T2, and we've done this Fourier transform. Okay, so we have different time domains. So these are all T1. So we have 1, 2, we keep incrementing them, and notice that it started small, so it started something greater than 0, but as we increment it, that signal got bigger, right? And these are just a series of experiments like we just went through, right? We did 4 experiments. Here's one experiment, here's a second experiment, here's a third experiment. Right? But we did a whole bunch, and it started going up, it went to a maximum, and then it came back through 0, and it went negative, through another 0 up here, positive, and so we're doing a whole bunch of, these are each a one-dimensional NMR experiment, each horizontal line. Okay? So this is a one-dimensional experiment. So we're just doing a series of one-dimensional experiments. Okay? Varying that T1 time domain that's in between the pulses. Okay? So if we look at this, this oscillating signal from the side view. So if we just looked at it, say from the side over here, we get something that looks like this, right? So we have our small signal here, and then it gets bigger, goes through a peak, and goes back down and up, and so we have this oscillating signal, which, if we add in relaxation and everything, gives us something that looks like this. But these are just the data points from the intensities of the peak in the one-dimensional experiment. But what does that look like? What else have we seen that looks like that?
It's pre-Fourier transform.
Right, it looks like the FID, the free induction decay, right?
It's a beautiful one.
Right. Well, we're just looking at a single point.
Okay.
We don't have a bunch of overlapping frequencies. Looks like an FID. Okay, so we Fourier transform that again to give us our second dimension. Okay, so we had one Fourier transform down here, and we do a second one over here. And what we get is a spectrum that has two different dimensions. Okay? The F2, frequency 2, comes from T2, which was our acquisition time. So that's kind of our normal one-dimensional experiment. Okay, this comes from the acquisition time. And then on this side over here, we have, this comes from the T1, the delta T1, and this was the time delay that we were varying between each of those one-dimensional experiments. Okay, and we get another peak in that direction because those one-dimensional experiments were oscillating at a certain frequency. Okay? So, we can draw this well, commonly in a couple of different ways. You can draw it like the one on the left, which sometimes looks cool when they do it like this, but they're not so useful. All right? Instead, what we do is we usually view them from above. And so we look straight down onto this, and we get this spectrum over on the right, which is called a contour plot, which is essentially just like a topographical map, right? So we're looking at it from above. Each of these are contour lines. The more there are, the taller the peak would be. Okay, just like looking at a mountain range on a topographical map.
But if you slice it horizontally, they're the 1D experiments, right? On the topographical.
If you slice it, well, not this way,
Yeah,
but down like this.
oh, it's that way? It's a
Yeah.
1D, not this way?
Now, if you do it like this, that's kind of a measure of like threshold or something.
I meant like coming out of the board.
This way?
Yep.
Well, that would be the same thing. We've got two dimensions like this, right? So essentially the cut like you're talking, well, actually if we cut it this way, what we see, this is a little flashlight shining on this side, what we would see would be essentially a shadow that looks like this peak over here. Okay, so this is what it looks like from the side. If we looked at it from this side, we could have another peak over here. These are the side views, are usually what are called the projections, and that's what you're saying. Like if you had a cursor that you could just move along like this, and the cursor would be like this, then you would see, whatever it sees along that one slice of the two-dimensional experiment. Right? If you have a cursor on a one-dimensional experiment, all it's doing is kind of following the peak here. In a cursor on a two-dimensional experiment, you would see, whatever it would be at that point. So this would be a cut like this, right? And if you did it right through the middle, then we'd see this. If you kept moving to the side, maybe you'd this is not perfectly symmetrical. You'd start to get off to the side, and then if you were all the way over to here, then you would see no signal anymore. Right? If you did it this way, you'd see something similar as well. And so the tip of the peak is right where these two meet at the top of the peak. Okay, so this spectrum over here is called a projection. And it essentially would be what we would see if we had the cursor running right through the tip of that peak. Okay, everybody with me? Okay, so we have quite a two-dimensional experiments that can be done, and in fact, well, the list is way bigger than this, right? But we're going to break them into two general categories. Okay, the first category are the homonuclear experiments. So this tells us that we're going to see interactions between two of the same type of nucleus. Okay, two nuclei. And so the most common are going to be the experiments that show interactions between protons. So homonuclear from one proton to another. All right, the first experiment we'll look at is called the COSY. You've probably maybe seen these before, but there's a bunch of different variants of that.
Did you say the last one?
What do you mean?
Toxin. The last one, how do you pronounce that?
Toxy.
You say toxin?
Yeah. And these are all, you know, what do you call them? They're all like abbreviations, you know. So that's like total correlation spectroscopy or something. The best one is that inadequate. We can have COSY, right, that is looking at coupling, so J coupling, and then NOSY is a type of experiment that looks similar, but it is looking at nuclear Overhauser effect, so through space interactions. There is a homonuclear experiment that shows coupling between C13 atoms. And that's a very powerful experiment, but as you might imagine, if it's a natural abundant C13, then it's very insensitive because you need to have two C13 atoms adjacent to each other in order to get coupling. Okay? And so the probability is very low. All right, and so then there are the heteronuclear experiments. And so the most common for us would be experiments that show coupling between protons and C13. Within these experiments, there are two different variations, and because we have two different nuclei, they differ based upon which nucleus is the one that we're going to detect. Okay, so we can either detect on the proton or detect on the C13. All right, most of these experiments started out detecting on C13. Okay, but that has the obvious disadvantage that C13 is much less sensitive. And so we don't really do those types of experiments very much anymore. So the first one was this het core. And so this gives us a one-bond coupling between protons and C13. So essentially it's telling us which protons are directly attached to which carbons. The het core is C13 detected. Okay, but these other two experiments, the HMQC, and I think mostly people run the HSQC, those are kind of analogous experiments. These are proton detected. Okay. for multiple bonds, so these are usually show 2-bond couplings and 3-bond couplings. So for example, they're good at showing, say, coupling between a proton and a carbon that's 2 bonds away, or a carbon that's 3 bonds away. The challenge is that even though we can try a little bit to optimize it for 2 or 3 bond couplings, we get a mixture of those. Okay, so that's a little bit of an ambiguity in our analysis, right? Because we don't always know whether it's a 2 bond or a 3 bond. Where this becomes especially useful is when our proton spin system is broken up, right? So for example, if this is a quaternary carbon here, and so we can't look at just proton couplings, right? Because there's no protons on that carbon. But the HMBC would allow us to look at proton to C13 coupling that bridges past the quaternary carbon. Okay, so we might have a proton spin system over here and a proton spin system over here that if we just looked at proton coupling, they're isolated from one another. But this experiment allows us to connect those two pieces together. Okay, another place that's especially useful is if instead of having a quaternary carbon there, let's just put Y here, we have some heteroatom. You know, it could be an oxygen or nitrogen or something like that, that we don't have any protons on, we can't see any coupling. But in the HMBC experiment, we can see coupling beyond that heteroatom. Like if we have a methoxy group, we can see where it's attached because we can see coupling between the methyl group and whatever carbon it's attached to. Okay? So there are, and there are other variations. I think what I'm going to do is we'll go through, most of our 2D experiments and get some practice and get going on interpreting these and everything. And then I had talked earlier in the semester with Casey about coming in and maybe either telling you about some newer things or some practical aspects of you guys going down and running these type of experiments yourselves. And we'll have him come in afterwards. All right, so let's look at, we're going to start with the homonuclear experiments. All right, and so here is what we would see if we have a COSY experiment. COSY stands for correlation spectroscopy. And the correlations are usually what we refer to as the interaction between the different protons. Okay? In this spectrum, this would be for at least a part of a spectrum where we have two signals that are two protons that are not coupled with each other. Okay, so there's no coupling in this experiment. So what we see, the way that this is drawn out, so it's a contour plot, right? We see two peaks, and the height of the peak is determined by the number of contour lines. Usually, oftentimes, sometimes these will be colored or something like that too. The one-dimensional experiment here essentially follows the diagonal. Okay, so this is what would be the one-dimensional experiment. Okay, the top here, this one, and over here, these are the projections. So this would be so this is going to be Usually I think F2 and F1. Let me make sure. Oh, I don't have it written into any of these. And so if we just looked at this spectrum from this direction, what we would see would be this projection up here on the top. Okay? If we looked at the experiment from this side, then we'd see this projection over here. Okay? So the projection, usually a two-dimensional experiment itself has less resolution than we would see in a one-dimensional proton experiment. Okay? And that has to do largely with the number of points that we're sampling. So we talked about before, if we did a one-dimensional proton experiment, we might sample, 16K or 32K of points to, and those points are outlining the peaks. But in a two-dimensional experiment, you're probably, I don't know what they do now on the instruments down here, but probably only like 2K of points or something like that. So the peaks are not sampled as much because you have to deal with 2 dimensions of data. So oftentimes, the actual projections would be what you would see if you were standing and looking from the side, or if we put a cursor through it. Okay? Oftentimes what we do, instead of putting actual projections on there, is that we just print off or print the one-dimensional spectrum along the two-dimensional axis. Okay, instead of the actual projection, because it shows us better resolution and it looks nicer and we can see the peaks better. Okay? If we have a these two signals that are actually coupled with each other, okay, then we see what we call off-diagonal peaks. Okay, so again, the one-dimensional experiment is along the diagonal. Okay, that's what we call the diagonal. And this is like our 1D experiment. Anything that's off the diagonal, so peaks here, anything that's off the diagonal is showing us coupling. Okay.
So does that include, those two, the one peak that's not
Within this little part here.
Yeah, is that just the one that's not a part of that diagonal? That's still.
You mean like this
Just that
one
one right
and
there.
this one? I think
Which
that
is
we include all of that as the diagonal.
Okay, because sometimes they get really close together.
Yeah, right. Well, and if we had these two peaks that were coupling each other and right next to each other, then it becomes complicated around around there.
Yeah.
So all of those 4 are not coupled, are part of the diagonal.
Yeah, we're going to call it part of the diagonal. Okay. So to look for coupling, what we do is we start with one signal and we would go vertically. We could go vertically this way until we run into one of these off-diagonal peaks, and then we go horizontally.
You went from the center?
I'm just going to the center of those. That's where the chemical shift would be, right in the center of a peak. Okay, so we can either go vertically and then horizontally, or we could go horizontally and then vertically, and we get back to the same peak. Okay, so we observe coupling by symmetrically situated off-diagonal peaks. Okay, so notice that those are symmetrical. We're essentially making a square here, as long as the axes are printed symmetrically as well. Okay, so the diagonal peaks are like the one-dimensional experiment. The symmetrically disposed off-diagonal peaks are showing us that this proton couples with this proton. Yeah.
So I was just gonna ask another, so one of the ways that I've done it is, well, I'll do the same thing, but with the actual peaks themselves. So like, so instead of having them go to the off diagonal, so sorry, going from the off diagonal to the diagonal, it would just go from the peaks down, and then so.
Just start here, you mean,
start-
and look this way
no,
and then this way?
No, from the peaks themselves.
Oh, yeah.
That's the way that's why I've done it. Would you prefer it if we did not do it that way, or?
Well, I think whenever we look at this, our tendency is going to be to look to here too. So if we know something about our one-dimensional experiment, then we're always going to be interested in, maybe we know what kind of a proton this is, right?
Yeah.
And so we're going to look down here and then see where it's coupled.
Okay.
No, I think you're...
As long as you show how you're doing it.
Yeah, right. We're not going to look at the diagonal peaks in a void without knowing anything about chemical shift or anything else like that.
Okay.
You live?
Early.
Dang.
I just have to come and get pictures and then I might head out.
All right, so off-diagonal peaks show coupling. Okay? So for a spectrum like this, it wouldn't really matter, right? We could see that they're coupled anyway. Right? We can measure the coupling constant and see that they match and everything. But this is going to be much more useful when the spectra get more complicated. Okay? Okay, so let's just take a look at this one. Okay, so here's the molecule on the left. And so what we would like to do is to try to assign which peaks are which. And so notice that they've printed the spectrum here, but we could take this same spectrum and tip it over here and print it along this axis as well. Right? So this peak, where they come together, is right here. Right? So there's two different axes, and remember that the diagonal right here is what really is correlated with that one-dimensional experiment. All right, so what I would recommend is that and notice that this is only going from 4.7 to 3.2 or 4.8 to 3.2. So for example, some of these signals out here and stuff are not included. Okay? But so let's look just around the ring. And I think the easiest thing to do, or the best thing maybe, is to try to pick out one proton on the ring, which we could maybe, choose which one would be most characteristic to pick out in the spectrum.
Easiest one, I guess, would be the first and the second. Like also on the far left, there's I guess it's hard to explain.
Yeah, no, I think. Well, look at the numbers.
Yeah. Oh, okay. Oh, I see.
The proton on which carbon do you think you can pick out in that spectrum? For example, which one of those protons would be this one at 4.6 that's the most downfield?
Probably
Number one.
Well, number one doesn't have any protons on it.
Number two.
Number 2 probably, right? Because it has an oxygen attached and it has that ester attached to it. Okay, so if we identify this one as H2, so then from that signal what we can do is we can go either vertically or horizontally over to here. We can go either way. And that tells us that the next proton over is H3. Okay, because that's showing us that those two protons are coupled with each other.
How did you get that H3 was coupled to it? By hitting the diagonal under H3?
Well, there's only one other thing proton that could be coupled to, which is 3. Right?
Right, H2
Yeah.
only couples to H3.
Because there's nothing on.
And that's why we go from H2 here, we go up or across, we hit the off-diagonal peak, and then we finish the square, and that points us to the next, to whatever proton it's coupling to.
So on the diagonal, even though that's a 1D, that tells us which proton it's coupled to.
Well, no, the off-diagonal ones tell us which diagonal peaks are coupled to each other.
Oh, okay. So we use the diagonal to help us figure out.
Well, the diagonal is what's associated with the one-dimensional experiment.
Oh, okay. Because I always
Okay,
associated
so
with
the off-diagonal is telling us that the proton that gives this signal is coupled to the proton that gives this signal.
Okay. I always used the, so if I had gone up first, I would have assigned that to H2 like you did, but I would have used the one on the off diagonal to say that's H2, and then go back to the diagonal, go above, and that would be H3. But this makes a lot more sense.
I didn't quite catch
Yeah.
what you said
That
there.
is
So
okay.
something was bouncing around in there, but yeah, so these are the actual signals.
Okay.
The off-diagonal ones are only showing us which signals are coupled to each other. Okay? So then we can do the same thing again, right? So then we go to the next one. We can go either vertically or horizontally. We go across. Notice that this next signal, though, this one has 2 signals in it. Right? It has one that's taller and then a smaller one right here. Notice when we look at this signal here and we look either up or we look down, notice that this signal is only like going to half of this. Right? This one is skinny and this one is fat. Right? That tells us that these fat ones are going to one signal here, the skinny one's going to a different signal. Okay, so the skinny one here would be going to the skinnier signal right up here. Okay, so when we have overlapping ones, we have to notice how those off-diagonal peaks line up. Okay, so we would say that this side right here is H4. Okay, just because this one is kind of skinny. And the other thing you could do, sometimes when you have them on paper, it helps to just like get a ruler or something, right? And lay it right through here and right through here, and notice that that one would be off to the side. The center of this one goes into the center of this other side over here. Right, or if you, even better yet, is if you have it on the computer, right? You can just move the cursor and see what lines up.
That's over.
Yeah. Okay, so that's H4. Now the tricky part here is it's hard for us to see what H4 is actually coupled to, because if it was just skinny like that, we don't see any other kind of skinny signals that are coupled to that. Right? So we could start here on the other side. So what do you think about these 2 signals?
We stop now going in that direction.
Huh?
We stop going in this direction now and then start on this side.
Yeah, that's what I'm
Just
gonna
see if
do.
it can help us.
Yeah, see if we can meet in the middle.
So when you run into a difficult spot like that, it's okay to just kind of abandon.
Well, yeah, you're going to always have different pieces, right? Just because we can have different spin systems within the molecule, not all of those spin systems are going to couple with each other, right? So ideally, that's what we'd like to do is we have, you know, and a proton spin system is going to be one that has protons on adjacent atoms usually, right? And then we might have an oxygen or a quaternary carbon or something that blocks our proton spin system. But if we can construct the different proton spin systems, then we'll go to the heteronuclear experiments to bridge those spin systems together. All right, so what do you think about those two that I have with the little bracket above it? If you were just looking at that without the 2D experiment, what would you think about those two protons? Yeah, I think they look like they're diastereotopic, right? And so which protons are diastereotopic on that molecule?
Number 6.
6, right? So these are probably H6. Notice that protons H6 couple with each other, right? So that makes sense. And then each of H6 can go to here and over to here. Or you could start with the other H6, let's do it in a different color, and go over to here and over to here. Both of those couple with H5. Okay, so those are H6. This is H5. But H5 and H4 are so close to each other in chemical shift, it's very difficult. You know, maybe the sides of this are showing coupling, but it's so close on the diagonal, it's difficult for us to see. All right?
H4, as you said, was a little skinnier,
Yeah.
so maybe it's a little not as.
Yeah, but it's hard to know whether
Yeah,
this square here is just coming from H5 or if H5 is a little smaller and those things are actually the off-diagonal peaks showing the coupling. So when two protons are coupled to each other and they are very close in chemical shift, it's still difficult for us to observe the coupling. Okay? Oh, we're way after already.
I gotta go get my picture taken. They're sticklers about this stuff.
You know, I think I signed up.
Emails this morning.
Oh, here, let me.